Hi there and welcome to another video from HEGARTYMATHS. It's Mr. Hegarty here, and in this video we're going to talk more about differentiation, and in this particular video about implicit differentiation. Okay, so what I'd like to be able for you to do at the end of this video is to differentiate implicit functions such as the following. And I want to start off by talking about what an implicit function might be. In order to do that, what does it, think about what implicit means in everyday English. Implicit means the thing is implied. It's not obvious, but you can get its meaning from within the context of reading between the lines, as it were. Now, to make it absolutely clear what this is, it would be easy for me to show you what explicit means. Now, an explicit function is something like this. It's something where y is the subject of the formula. Something like y is equal to x cubed add 4. That is an explicit function because y is given in terms of x's, just x's and numbers, no other complications. And if I was to differentiate this, dy by dx, nice and simply, would be 3x squared. Again, my y is given in terms of some function of x, and my y dashed, when I've differentiated it, is some other function with just x's in it. Okay, so that's what explicit means. It means basically y is the subject of the formula, y can be given in terms of x and x alone, and you can find dy by dx in terms of x and x alone. So, what do we think implicit means then? Well, implicit means that maybe y isn't the subject of the formula, and maybe y is given in terms of x's and y's, for example. So something like this maybe, x squared add y squared is equal to 6 take away y. Now, in this case, y is not necessarily the subject of the formula. I suppose we could make it the subject of the formula, but it isn't instantly the subject of the formula. And when I find, y dashed or dy by dx, it may be in terms of x's and y's. So the difference here is my dy by dx, when I eventually find it, it may be a function of x, but also have y's in it. Just like my original function here has got x's and y's in it. So originally, my dy by dx in explicit functions, I can usually make y just in terms of x, and my dy by dx is just in terms of x. Here, my x isn't necessarily the subject of the formula. It's bound up with x's, y's, and other x's and y's, and functions of x's and y's. And when I work out dy by dx, it may be in terms of both x and y. So it's implicit. It's not separated from the x's, as it were. So that's what implicit is. How do we implicitly differentiate? Well, we use the chain rule. And I'm going to show you two very simple cases. So these are the building blocks of everything we need in this chapter. So case 1. We didn't even know this could be implicit differentiation, but let's do it anyway. Suppose y is equal to x cubed add 4. And we differentiate both sides with respect to x. So we do d by dx of y, and we do d by dx of this thing here. Now, we've never really talked about this before. There was no real need to, but it allows me to develop the ideas further. This is easy. Everything's in terms of x. Now, if I differentiate with respect to x, I would simply get 3x squared. Now, here, can I differentiate y with respect to x when y is a different variable? Well, what I could do, a way of thinking about it, I could differentiate the y with respect to y, instead, pretend I was differentiating with respect to y, and then multiply afterwards by dy by dx. And the reason sort of you can think of this as holding true, the dy on the denominator there and the numerator there, you can sort of think of them cancelling, and we're left with d by dx of y. Now, I can actually differentiate y with respect to y. It's 1. So this is just 1 dy by dx is equal to 3x squared, i.e. dy by dx is equal to 3x squared. Now, we've never actually bothered to think about differentiation in this regard before, because when I differentiate y with respect to x, I've just sort of got used to the fact that I get dy by dx. Where this becomes really useful is if this isn't just a single y, it's something else. So let me give you an example, case 2. Suppose we had y squared is equal to x cubed, add 4. And I wanted to differentiate both sides with respect to x. Now in this case, it's not as simple as it was before. I know that d by dx of y is dy by dx, but what's d by dx of y squared? Well, what I can do, like I did before, I can trick myself in a way to differentiating it with respect to y, but then post-multiplying afterwards by dy by dx, because we can think of it as the dy sort of cancelling and it leaving us with the thing we wanted. And this here would therefore be 3x squared as it was before. Now d by dy of y squared is actually 2y. So we have 2y dy by dx is equal to 3x squared. And so making dy by dx the subject, dy by dx would be 3x squared divided by 2y, provided obviously y wasn't 0. So this is when this case became really useful. Okay, now the last thing to consider, what if I asked you, case 3, what if I asked you to differentiate something like 4x squared y cubed equals 8? Imagine I asked you to differentiate something like that. So we differentiated both sides with respect to x. Now, differentiating a number is obviously 0. And this now, I could think of this as the product rule. There is a function multiplied by another function. So, you know with the product rule, uv, it's usually uv dash plus vu dash. So I can think of this as u, which is 4x squared, and differentiate the y cubed, plus the v left alone, so y cubed, and I differentiate the 4x squared. So I'm using the product rule here. Now, how would I do this? Well, this second bit's easy. Y cubed, differentiating 4x squared with respect to x is easy. It's 8x. That still equals 0. Now, this one is slightly more complicated. The 4x squared is just thought of outside the front, it's a constant. I'm going to, instead of differentiating y cubed with respect to x, I'm going to trick myself and differentiate it with respect to y, but then post-multiply by dy by dx, because we can think of it as the dy is kind of cancelling and giving us what we wanted. So therefore this would be 4x squared, differentiate this would be 3y squared dy by dx, plus, and this would be 8xy cubed is equal 0. And then what we can do is we can make dy by dx the subject. So dy by dx here, I would subtract this off both sides, so subtract 8y cubed, and I would end up dividing by 12x squared y squared, so 12x squared y squared. And I could cancel as appropriate. I think I would get 4 goes into top and bottom and x, so I get negative 2y over 3x, something like that. Okay, so that would be my dy by dx in that case. Okay, now they're the ideas we need to do all these questions. Firstly, the simplest case, we kind of could think of normal differentiation when we do d by dx, when we differentiate y as an implicit, but we never thought of it like that. It's more useful when y is some power or some function, so you have a function of y, and then we need to think of it when there is a function of x multiplied by a function of y and how to do that. So they're the 3 ideas we need. Let's do 3 questions. We're asked to find dy by dx in terms of x and y when the following is true. So what we're going to do is we're going to differentiate both sides of this. So we're going to differentiate x cubed plus x plus y cubed plus 3y, and we're going to say this is equal to the differential of 6. So I'm differentiating both sides. And I can apply the differential through to each thing that's being added. So I can say that's d by dx of x cubed plus d by dx of x plus d by dx of y cubed plus d by dx of 3y, and I know this is equal to 0 because differentiating a number always gives me 0. Okay, now I can differentiate these two with respect to x because they're functions of x, So that would be 3x squared add 1, these two. Now this one, I need to be a little bit more careful. I'm going to trick myself into differentiating it with respect to y because it's a function of y, but multiply afterwards by dy by dx. And I'm going to do the exact same here. I'm going to trick myself into differentiating it with respect to y, but then post multiply afterwards by dy by dx. And I know that's going to be equal to 0. And now we can do these two differentials here. So we can say that 3x squared add 1, and then differentiating this, it would be 3y squared dy by dx, so it would be plus 3y squared dy by dx. And this here would be plus 3 dy by dx is going to be equal to 0. And I can tidy everything up and make dy by dx the subject. So firstly, I could factorise the dy by dx from both these two terms here, and I'd get 3y squared add 3. And I could subtract this off both sides. So I could subtract 3x squared, subtract 1, and then I could say that dy by dx would be negative 3x squared, subtract 1, all divided by 3y squared add 3. And therefore I have dy by dx in terms of x and y, just as like I've asked for. Okay, so that's the first one done. Let's have a go at another one. We're asked to find the value of dy by dx at the point where x is 1 and y is equal to 1, where we have y bound up in this implicit equation. So what we're going to do, to find dy by dx, we're going to write our original equation, 4xy squared plus 6x squared over y is equal to 10, and we're going to differentiate everything with respect to x. So I'm going to differentiate this, I'm going to differentiate this, and I'm going to differentiate this. Now, we're going to have to do each one separately because there's quite a lot of working for each one. So firstly, working 1, let's do the d by dx of 4xy squared. Now, I need to think of this as a product, where that's u and that's my v. And when I differentiate this, I'm going to say that it's going to equal u v dash plus v u dash. So it's going to be equal to u multiplied by this differentiated, so 4x, and then the differential d by dx of y squared, plus v multiplied by this differentiated, so y squared multiplied by d by dx of the 4x. And how do I do this? Well, I can leave the 4x there. I have to trick myself into thinking this is d by dy of y squared multiplied by dy by dx. Because it's a function of y, I'm going to differentiate with respect to y and multiply afterwards by dy by dx. But this one I can differentiate straight off and it will be 4, so plus 4y squared. This off, d by dy of y squared is going to be 2y, so this would be 8xy, so we'd have 8xy dy by dx plus 4y squared. So when we differentiate the first component, 4xy squared, I got the following. Now working 2, I'm going to have to differentiate this thing here. So let's do a different coloured pen here, working 2. I want to work out d by dx of a quotient, of a fraction. So it's 6x squared divided by y. 6x squared divided by y. Now you should realise that's u divided by v, and applying the quotient rule, this would be vu dash subtract uv dash all divided by v squared. I.e. that means v, which is y, and the differential of u, which is d by dx of 6x squared, take away u, which is 6x squared, and the differential d by dx of v, which is y, and all of that divided by v squared, which would be y squared. So tidying that up, this differentiate is clearly 12x, and multiplied by the y we'd get 12xy. This here stays as 6x squared, but d by dx of y is just dy by dx. So we get subtract 6x squared dy by dx, all divided by y squared. So this was the second component, d by dx of 6x squared over y. So now we're ready to write this down, and write equals 0 down. So what we can say, therefore, we can say that 8xy dy by dx, so the first component, 8xy dy by dx, plus 4y squared plus 4y squared plus this thing we've just worked out, so 12xy subtract 6x squared dy by dx, all of that divided by y squared is equal to d by dx of a number which is just 0. Now, we could try and make dy by dx the subject, but what's the point? We're not asked to make dy by dx the subject, we're asked to find dy by dx when x is 1 and y is 1. So let's at this point substitute in x equals 1 and y equals 1 now, before we start getting confused with our algebra. So let's do that. What would we have? We'd have 8 multiplied by 1 multiplied by 1 dy by dx plus 4 multiplied by 1 squared plus 12 multiplied by 1 multiplied by 1 subtract 6 multiplied by 1 squared dy by dx, and all of that over 1 squared. And all of that would be equal to 0. Now the reason this is preferable is this will tidy up nicely. Let's have a go at showing that. 8 multiplied by 1 multiplied by 1 is just 8 dy by dx plus 4 multiplied by 1 squared is just 4 plus here we've got 12 multiplied by 1 multiplied by 1 is 12. Take away 6 dy by dx all over 1. So that's just 12 subtract 6 dy by dx is equal to 0. So how many dy by dx's have we got? Well, we've got 8 of them. Take away 6 of them. So we've got 2 dy by dx's. And we have also got plus 4 plus 12. So that's going to be plus 16. So plus 16 is equal to 0. And making dy by dx the subject, dy by dx is therefore negative 16 over 2, i.e. dy by dx is equal to negative 8. And what did it ask us? It asked us what is dy by dx at that point. We've just found dy by dx is equal to negative 8. Okay, last one here. Find the value of dy by dx at x is 1 and y is 1 when the following is true. So exactly like before, just a different type of function. So let's write this down. So we've got e to the 2x, natural logarithm of y, is going to equal x plus y take away 2. Now I'm going to differentiate everything. So I'm going to differentiate this side. I'm going to differentiate the x. I'm going to differentiate the y. And I'm going to differentiate the 2. Okay? Now, this is a product rule here. You can think of this as u and v. So it's going to be, we're going to use uv dash plus vu dash when we differentiate that. i.e., keep u as it is, so e to the 2x, and we're going to differentiate with respect to x, the y, and we're going to add, sorry, not the y, the ln y, the natural logarithm of y, and then what we're going to do is we're going to keep the natural logarithm of y as it is, and we're going to differentiate e to the 2x. So that's applying the product rule, and this is going to be equal to d by dx of x is just 1, d by dx of y is dy by dx, and take away d by dx of 2, which is just 0. Okay, so let's actually go ahead and just do these differentials. Now, this one's still going to be e to the 2x. Now, instead of differentiating this natural logarithm of y with respect to x, I'm going to differentiate with respect to y, and I'm going to multiply afterwards by dy by dx as a sort of a fix. And this one here is going to be plus ln y, and the difference of this is 2e to the 2x. So I'm going to put the 2 there and e to the 2x, and that's going to be equal 1 plus dy by dx. Okay, so nearly there. So this is going to be e to the 2x. Differentiate ln y is 1 over y. So I'm going to say that's e to the 2x over y multiplied by dy by dx plus 2 ln y e to the 2x is equal to 1 plus dy by dx. Okay, now, it didn't ask us to make dy by dx the subject. It said find its value when x is 1, y is 1. So let's do as we did before. Let's substitute x is 1 and y is 1 in here. So what do we have? Well, we'd have e to the power of 2 divided by 1 multiplied by dy by dx plus 2 ln 1 e to the 2 is equal to 1 plus dy by dx. Now, ln 1 is 0, so all of this would be 0. and this would just be e squared dy by dx. So what we'd have is we'd have e squared dy by dx is equal to 1 plus dy by dx. Subtracting dy by dx off both sides, we have e squared dy by dx subtract the dy by dx is equal to 1. Factorising your dy by dx would be, factorise that would be dy by dx multiplied by e squared take away 1 is 1. And therefore dy by dx as the subject, dy by dx would therefore be equal to 1 divided by e squared take away 1. And we have found our dy by dx at x is 1 and y is 1, and we're done. So that's it for this video. Make sure you do the following just to consolidate the work we've done here. Thanks for watching.